first really spring morning of the year, I think it's safe to say, outside in southern Wisconsin today. You'll see some evidence for that as we go through some of the observations. But here's the surface map from this morning at 8:13 local time. We've got a pretty decent cyclone off the coast of Newfoundland and Nova Scotia, and we'll see that really nicely illustrated in the satellite in just a minute. Then a region of high pressure sitting over the southeastern United States, a sort of a broadly dispersed region of low pressure over the central United States. I think it may be biased a little bit towards the west coast, and then a ridge of high pressure building in to the Pacific Northwest. And the reason I point out all four of those features is because I'll make the point when we go to the 500 millibar map, which today is from the Canadian Meteorological Center. Our maps here in the department were not working this morning, so I got some maps from Canada. And they're going to show this beautiful relationship that we've been talking about in class. First of all, look at the wave-like nature of the disturbances. There's a cyclone off the east coast, an anticyclone along the coast, a broad region of cyclonic-type conditions, region of low pressure in South Dakota, and then anticyclonic, high-pressure conditions to the west. So it's low, high, just as we've been talking about in sequence. And that means there's probably a sequence of waves at upper levels. And we've talked now about the vorticity, the curvature in the flow particularly, and we'll see that evident in the 500 millibar flow. Lots of curvature in the flow across the continental North America. And downstream of the trough regions of curvature, the counterclockwise regions of curvature, that's where our cyclones are. And downstream of the ridges, the clockwise regions of curvature, that's where our anticyclones will be. So today, the map's chosen at random. It just happens to be today, and you're going to see these relationships vividly illustrated once again. So it's a really robust set of relationships that we've been talking about in class. So there's our surface map. We are not far away from some pretty active shower activity just to the south and west of us near Platteville, maybe on the border of Iowa. I don't think we're going to see any of that rain during the day today, although that's now a little bit more in doubt than it was when I woke up this morning. I think we may see a shower, but I would put it at a low probability. Tomorrow is a much better day for a chance of showers, as this whole weather system that is now currently not too well organized is going to become a bit better organized as it moves to the east. So now let's look at the temperatures. Yesterday we had a high temperature of 75 degrees, which was only 2 degrees shy of a nearly 100-year-old record. We had set the record for 77 in 1929 here in Madison on April 4th. We almost did it yesterday. A little bit of high clouds at the end of the day might have been the thing that kept us from getting those extra 2 degrees, maybe even soil moisture, I suppose. But a bunch of little things contributed to us coming just shy of a nearly 100-year record. But hard to complain with the weekend. Weather was beautiful. Here's the surface temperature this morning, and again at 8 o'clock local time, 61 degrees in Madison at 8 a.m. It hasn't been 61 degrees at any time of day until the last couple of weeks, let alone at 8 a.m. So absolutely beautiful morning. You can smell the spring. You know how the ground has a certain scent to it when the air is moist and warm, and that's an actual thing. That's not just a perception. That's real. There's some biomes that get released when the air warms up and the ground warms up that actually have that sweet fragrance. So there's some real physical reality to that. It isn't just your perception. 61 this morning. Look at broadly 60 degrees or close to it all the way from the Texas Gulf Coast up to Madison. So we're talking about being in an air mass that's effectively the same air mass that they're enjoying down in Del Rio, Texas, or in Brownsville, Texas, just about this morning. So pretty wild. A little cooler in New England and a little cooler in the Pacific Northwest, but this is, don't forget, pretty early in the morning for them. It's 6 a.m. So we had yesterday, our 6 a.m. temperature was about 34, which was barely different from average, and then our high was 23 degrees above the daily average. So we started out cool but warmed up fast. That can happen in April. Here's the dew points that go along with that. Remember, we had a 61 degree temperature in Madison, 50 degree dew point, so that's a lot of water vapor. This is about the highest dew point I think we've had all season. Certainly, it feels like it when you walk outside. And once again, all the way from the south coast of the Gulf Coast of Texas, just about all the way up to Madison, dew points are uniformly in the low to mid 50s, a few high ones, 60 at Houston, 62 at Victoria. Other than that, we have some pretty uniform dew points. So as I said, this air mass that we're experiencing today is really not different from anything you'd experience if you traveled 1,500 miles to the south-southwest. Unbelievable, isn't it, how uniform that is? And then quite drier where it's cooler, both in Seattle and even more so in the New England area. 15 degree dew point in Boston, very dry day today for them to start out. So we have a dew point that's nearly as high as the dew point in Miami right now. So that's pretty good. That doesn't happen very often around here. Okay, so that's our broad picture of the upper level, the surface charts. I want to now show you the Canadian Meteorological Center 500 millibar map. So let me put this this in a full picture. So this is from last night at 7 p.m. We didn't get the 7 a.m. map yet. So it's a little bit different than the 500 millibar maps that I've been showing you before because the lines look a little different. We have red ones and black ones on the maps we make in our department. I want you to just concentrate on these thick and then solid black lines. Those are the so-called geopotential height lines. They're the equivalent of isobars at the 500 millibar level, which is about 3 miles above the surface. So here's what it looked like last night. And you can see there's kind of a big ridge off the west coast, a trough draping across the Pacific Northwest, actually going all the way into the Central Pacific, then a flat ridge over the continental United States, and then a decent trough off the east coast, cutting right through the state of Maine, and then there's this upper-level cyclone, cut-off cyclone off of Nova Scotia. So at the next time, or not the next time, I just want to point out the trough axes. Here's one trough axis, and I could have extended this all the way down to here. I just chose not to for reasons I'll describe in a minute. So there's one trough axis draped across Western Canada and the Pacific Northwest. Here's another one that comes all the way from the Canadian archipelago into the maritime provinces of Canada. So that's pretty obvious. And then here are the ridge axes. Here's a ridge axis that goes all the way from the northern Yukon territories down to well south of the Aleutian chain. And there's all geopotential height or pressure ridging right along this line. And then there's this flat ridge axis where the geopotential height lines, the black lines, the equivalent isobars, bulge poleward across this whole line as you move up to the north and east. So that's evidence of the ridge trough structure, the waviness in the mid-latitude flow. And then if we put the vorticity in a very crude proxy on top of that, here is the cyclonic vorticity, which would occupy the trough axes. The flow is coming around the bend in a counterclockwise fashion, so that's like a vorticity maxima at the northwest United States trough. Here's another flow coming around in a counterclockwise fashion around this cutoff, so there's another vorticity maxima, cyclonic vorticity maxima, positive vorticity. And then here is a region where the flow is turning clockwise at upper levels. You can see it's coming across from the west, and then it heads to the south. So there's a clockwise turn, and that's a ridge axis, and there's negative vorticity. And here's another ridge axis, and that's negative vorticity as well. So one sees, perhaps more obviously in this cartoony version of the vorticity, the fact that the flow has a ridge, a trough, a ridge, and a trough in sequence in the middle latitudes across North America last night. And then let's go back to what we were talking about in class, the fact that our downstream of our ridge axes, downstream of the negative vorticity maxima in yellow, we ought to see regions of high pressure developing at the surface because there's upper level convergence as a consequence of that negative vorticity advection, and then the air sinks, and sinking air clears out the sky and also tends to fill the column with mass, and that means that the pressure rises at the bottom. The opposite is true to the east of the upper level trough axes, where since there's positive vorticity advection, that induces upper level divergence of the flow, and that means the air rises from the ground up to that level, and the rising air, of course, cools as it expands and condenses any water vapor and it turns it into clouds and precipitation. So we see cyclones, regions of low pressure to the east of upper level vorticity maxima. So let's see. Here's where our surface cyclones were, if you remember from the surface map. One of them was over just off the coast of Nova Scotia and Newfoundland. The other was over Montana. This was the broad region of not so well organized low pressure, but kind of centered around central Montana. And they're both perfectly correspondent to their upper level vorticity structures at the same time. And then our regions of high pressure, one of them was over the southeast United States. That's to the east or downstream of the broad upper negative vorticity feature in this flat ridge over the continental U.S. And then remember I said there's high pressure building in over the Pacific Northwest. Here it comes. Here's the region of high pressure last night. Today it's firmly over Washington and Oregon. Last night it was a little bit further to the north and west, but it was also immediately downstream or to the east of the region of negative vorticity at upper levels. So this is a robust set of relationships that we've been looking at in class, and it's so robust that I can pick a map effectively at random and show you the exact same thing again, and which I just did. So let's see how some of these features look on the satellite movie. Here's the infrared satellite movie over the continental United States and adjacent waters. Look at this, right away, right off the Canadian Maritimes. There's our cyclone. And that's where we had that upper level 500 millibar vorticity maxima, and just to its east was where the surface cyclone was. And you can see there's a beautiful relationship between those two right there. Over the southeastern United States, very little cloudiness. Why? Because there's negative vorticity advection occurring at upper levels, producing a region of high pressure at the surface, and that's a function of subsidence gently sinking air, and there's no clouds down there. So that's nice. Then we had our broad region of unsettled weather over the central U.S., perhaps focused over central Montana. And look at, that's where all the cloudiness seems to be. And that was immediately to the east of the next upper level trough feature in the Pacific Northwest. And then notice how it's clearing over Washington and Oregon. That's as the high pressure builds in with the southward sagging of that next upstream region of ridginess, negative vorticity advection. So it's really clear once you see these things on a variety of different analyses that they do in fact show up in the traditional ways of looking at things that we've been doing all through the semester. So I hope that you're as excited about this as I am, because I feel like I can really start to put all these pieces of the puzzle together for you, and I know that must be exciting for you if you have an interest in this. But it really is true, all these things are there. So let's take a look at the radar across the continental U.S. Here's a little bit of precipitation over Maine that's associated with that cyclone that's not on this map. It's a little bit further to the east off the Maritimes. So there's some evidence of that being a precipitating feature. Not sure there's any real precipitation going on down over the southern coast. These little lines that seem to come out of the Birmingham radar just mean they've turned it way up to be sensitive. I think they have low-level fog down there today. That's another fact, another characteristic of regions of high pressure at this time of year. Traps the low-level air. And so if it's already moist, the stability just above the ground gets quite high because the air is sinking and warming up, and it's hard to mix it out. So you can get thick fog down there, and that might be why they've turned the radars up. Here's some interesting convective weather roaring across central Michigan, just to the south of Chicago, and then right along the Wisconsin, Illinois, and Iowa border. So we're just to the north of some pretty active weather this morning. That's quite interesting. Didn't expect it. I thought it was going to be more tomorrow, early in the morning, and then through the day tomorrow. And then here's the only place where it seems to be precipitating in that whole region in the Intermountain West is right there in central Montana, which is probably the region that's getting the most intense positive vorticity advection from that upper level trough that we talked about. So it's really nice. Even on the radar, you can see all of these features reflected in one way or another. And then here is the West Coast satellite image. And you might have remembered my trough axis that I drew through central Canada off the California coast. I said I could have extended, or through the Pacific Northwest, I could have extended it into a cutoff low that was off the coast. And you can see that feature evident in this swirling mass of clouds well off the California coast in the satellite movie. And then in between the next cloud system that's at the moment in northern Canada, northern British Columbia, there's this broad region of clearing, and that's the region of negative vorticity advection associated with the ridginess that I showed in the 500 millibar map. So it's a nice day for Seattle and Portland today. So good for them. And then some cyclonic activity well to the west. It's even west of Hawaii, so it's past the date line, and that's in the central Pacific Ocean. But a fairly benign looking Pacific across the basin today. So lots of things happening, lots of things coming together in the series of lectures. I hope you're enjoying that.